Hi, I'm Fabian Schneider, I'm with NEC, and today I'm going to present what we did as implementation work for the Aspen project. The Aspen project is all about helping real-time media applications communicate their demands for prioritized communication to the network. So let me go through some slides to show that. So the motivation is that typically when we are looking at unified communication systems, we have end devices that need to communicate with each other, and a popular means today to facilitate such communications is to mark packets and have those marked packets be treated with priority. So with today's systems, typically what you have is the end systems will mark the packets, but usually you don't want to trust those end devices in marking the packets correctly, because if a user realizes that properly marked packets get priority treatment, he will just start marking all his traffic. So we rather want to trust the unified communications infrastructure here, and therefore we need an interface between the real-time media infrastructure and the network, in our case the SDN controller. So let me quickly show you what we did here is the ONF provided an specification for an application in order to allow this communication to happen. And we show a proof of concept implementation that we did based on several open source tools and some contributions to the open source SDN org platform that the ONF is hosting. So the scenario that we are looking at is basically like this. So you have in the middle a legacy network which is QoS aware, which is reacting to marked packets. This legacy network does not have to be SDN controlled and can be basically reused from what was deployed before. We also assume a single operator domain deployment where we don't need to work across multiple administrative domains. So what we have here, as I said, we have the end devices and we have the real-time media infrastructure, and the network in between is kind of gated by OpenFlow controlled switches, which will push the proper markings to the packets. And then we'll have the real-time media infrastructure communicate with the SDN controller through a real-time media network service. And this is a new component that we developed for this project and contributed. So to just have a quick look at the architecture and the use components of this implementation, we have at the very bottom, we have the network, which is run through Mininet and OVS. On the top layer, we have Open Daylight in this case, which is then exposing a VTN interface to our newly created network service, which is our contribution to the open source SDN world. And on top of that, we are currently using Video LAN client as a representative for real-time media applications, basically. The Video LAN client we configured in a way that it is reporting whatever it's doing into a log file, and from that log file we have a parser script that is going over it to record and extract when things are happening. So for the scenarios that we are having here, we have this very simple topology where we have some hosts on the left and some hosts on the right. We do generate background traffic from host 2 to host 5 in this case, which will use up all the available bandwidth that is provisioned on a bottleneck link here. This switch in the middle is configured to prioritize properly marked packets. And then we have video traffic running across here as well, and the combination of those two would exceed the bandwidth limitations of the link. So we need to prioritize traffic in order to show a proper good output. And that's basically what we're seeing here. So I just see the video looped around, so now let's go into the demonstration a bit here. So what we can see right now is there's a video playing, and it has been playing already. At the very bottom here we have the cross-traffic generation, or the background traffic generation. This is the sender window from which the stream is originated. Here we see the receiver side, which is playing the video. At that point here, you can see that our log file wrapper basically recorded and already provisioned the first session. And here in our network service, very easy GUI, we see one session provisioned with an ID, and it goes from the .1 to the .6, which I exactly sees two hosts. At the very bottom, we have a shell for the network emulation, but this is just running. So in order to show that something is actually happening, and that there is, and it's not just like a mock-up of everything, what I'll do now is I will remove this provision session so that we should see that the video quality degrades and we start losing packets. And for that I quickly need to go here and type in 17146, right? So I deleted the session now, and you can already see there are some reports coming in, lost packets, and the video quality degraded. So basically, without the provisioning that was happening automatically, we don't achieve the quality that we want. So now, in order to really show that there's background happening and impairing this traffic, I will just stop the background traffic. And that should restore the video to a good quality, because now we don't have any competing traffic anymore. So in order to really, to again show that everything is working as planned, let me just stop the video stream completely for the time being. Let me set back the background traffic, and what I'll do now is I'll show you how the automatic provisioning will happen by just starting the video stream. Now let's start over this thing and watch the automatic provisioning of everything. You will see a video screen popping up right now when I start the session now. Right, here we go. And as you can see, the video is playing nicely. You see here the automatic provisioning took place. The log file viewer was extracting the request, pushing it down to the network service, which was provisioning the session. What we can see is a nice and clear video. And with that, I conclude my presentation of our implementation here. And thanks for your attention.